Hello and welcome. In this video, we are going to do Exergy analysis of a closed process. Obviously, an understanding of a closed process analysis is needed before we can perform an Exergy analysis. In fact, we'll take the same problem that we analyzed in that video and expand that to include Exergy analysis. Exergy is covered in chapter 6 in test and in the textbook. We have already discussed what is a closed process. System is closed, it's unsteady, and it goes from a beginning to final state. And we are going to do an Exergy inventory of this process. In other words, where does Exergy enter, where does Exergy leave, where is Exergy stored, etc. To do so, let me just quickly go over a few slides to explain what Exergy is all about. So here is a closed system at a high pressure and temperature, and as you can see, this contraption extracts useful work out of the system. In other words, Exergy is basically how much useful work you can extract out of a system. That's called the variable phi. It essentially tells you exactly how much energy you can extract, how much useful energy is there to squeeze out of a system. So that immediately brings up the concept of a dead state. When the system goes to dead state, it is considered to have zero Exergy. So this concept is heavily utilized in Exergy equations. So this is the Exergy balance equation, for instance. It keeps track of useful energy of the system. And as you can see in this animation, it just explains the Exergy balance equation in a graphical way, that Exergy in this balloon in the system can be seen to increase with time because Exergy can enter with a flow shown by this gray arrow. Exergy can leave with a flow carried by the flow. These are called transport terms. Exergy can enter because of heat transfer at a temperature higher than ambient temperature. Also, Exergy can be taken out by useful work. Of course, that's pure Exergy. So a balance of that is shown by these differential equations, and this equation is integrated for a closed process. For instance, this is a very simple closed process. Here, a system is losing heat, I believe. It's electrical heating of water. And here's the system. If you want to take a look, we are just heating water with electricity. And these are different diagrams. I'll just jump to the Exergy diagram. So in other words, electricity is pumping in Exergy into my system. That's why the Exergy of the system is increasing. But a big part of Exergy is getting destroyed. It's very possible Exergy can be destroyed because of entropy generation. Exergy could also leave by heat, but in this case, the temperature is ambient temperature. Therefore, no Exergy is leaving to the atmosphere. Basically, Exergy cannot be stored in the atmosphere. It's already in dead state. Okay, to solve an example, let's go to test steps module and launch a closed system generic branch. And we follow the closed generic branch, simple process, and launch the PG model. In the hands-on examples, there will be several Exergy related examples posted soon, but let's go to the app page and let's recreate the problem we already solved. If you recall, we were heating air at 100 kPa, 300 Kelvin, and the volume was 1 meter cube, and we heated it up to 3 times the original volume at the same pressure, 100 kPa, and of course we know that the mass doesn't change for a closed system. And without Exergy solution, we solved the problem. Just to recreate that solution, if you recall, we load the inlet and exit states, beginning and final states. Here are the mass, energy, entropy equations, and they are solved as soon as we click calculate. You notice that entropy generation is negative here. That's because the boundary temperature is set at 298. You cannot heat a gas to 1000 Kelvin, close to 900 Kelvin, if the boundary temperature is 298 Kelvin. So suppose the boundary temperature is 1000 Kelvin, you will find the entropy generation becomes positive. Okay, so let's keep this in mind and let's go back and try to understand the Exergy solutions or Exergy inventory. You click the include Exergy and you'll notice phi and psi shows up. Phi is the Exergy per unit mass of the system. Of course, they are not calculated because to calculate Exergy you need the dead state because Exergy is a measure of how much difference the system possesses compared to its dead state. So we go to state 0, which is the designated dead state, and let's say 100 kPa and 300 Kelvin is the atmospheric conditions. Of course, velocity and height has to be 0 to be at the dead state. State 1, which happens to be the same condition as atmospheric, obviously has 0 Exergy, but notice state 2, which is a higher temperature, 900 Kelvin, has an Exergy. So what is the stored Exergy of the system now? Phi times the mass of the system is the total stored Exergy. In other words, so many kilojoules are converted to kilowatt hours, so much electricity you can make out of this system at the most. Okay, let's go to the process panel. This time, the process panel looks much more complicated because Exergy has been added. First thing to notice, the Exergy equation shows up. That is which is the increase in Exergy is equals the Exergy, the rate at which the Exergy enters the system through heat minus Exergy taken out through useful work and Exergy destroyed by irreversibilities. And they follow the same pattern for closed process as energy and entropy equations. Notice that the system schematic process schematic has been modified because the system before had only one boundary temperature. Now notice we have divided that into two boundary temperature, TB, a source other than atmosphere, and T0 is of course atmosphere. So we can assign values to T0 is picked up from state 0, but TB we can assign a value. Right now default TB is 298, but let's say we assign it a temperature of, let's say, 1000 Kelvin. We'll notice that, okay, now let's load state 1 and state 2. These are our anchor states, beginning and final state. This is our boundary temperature where the heat is coming from. And let's solve this equation, see what we get. We got all these variables. It's sort of crowded, so let me just highlight the important variables here. So we are heating, if you notice, from a reservoir B at temperature 1000 Kelvin, and this is the amount of heat that goes in. There is no atmospheric heat loss, therefore Q and QB are the same. As the system expands, there is an external work transfer of 200 kilojoules, but all of that goes to atmosphere, as you can see, because it's at the constant pressure of atmosphere, the system is expanding. So all the work the system does is not useful. Therefore, the useful work should be 0. And if you notice, because of the heating of the system, phi Q, this is the amount of Exergy that is stored in the system. Just like delta is the energy stored in the system, delta S is the entropy stored in the system. This is the Exergy that is stored in the system. I'm sorry, this is the Exergy that came in with heat, and this is the Exergy that has been stored. So you can see that this is kind of the desired Exergy change, and this is what we paid for. So this is the ratio of the two is called exergetic efficiency or second law efficiency sometimes. And you'll notice this is the Exergy that entered the system, and this is the Exergy that was stored, and no Exergy came out as useful work. Therefore, the difference must be what is known as irreversibility. If we had no irreversibility, obviously the system could produce useful work, and that's called the reversible work. Anyways, there is a lot to learn from these numbers, and if you have a thorough knowledge of Exergy equations, you'll realize how easy it is to use this app to figure out where all Exergies are going, where all Exergies are stored, and how Exergy is destroyed. So as you see more examples, you will realize how to use this quite easily. One more thing, that if you use the super calculate button, you get all your test codes and you can regenerate the solution very easily from this small amount of data.